All right, so this is the follow-up part to the relative velocity 1D motion. This will be the 2D motion part, and this will be from the same note guide, and so you should have that open. So this logic and what we have written here applies to 2D motion, the same logic that we used in 1D. But we should remember that when we add in 2D motion, right, that we put the vectors head to tail, but we have to use Pythagorean theorem. So like if you think like a 3, 4, 5 right triangle, vector 3 plus vector 4 does not directly equal vector 5, right? 3 plus 4 is 7, but 3 squared plus 4 squared equals 5 squared is what I'm saying. Okay, so we're going to have that happening here. So I'll point that out here in a second. Let's go ahead and look at the situation. This is a river problem. We get a lot of these. You'll have one of these problems on your test. And when you get a problem like this, I always draw it the same way. And so we'll start by drawing a river. It's kind of what I have there. I guess I can put some blue in here if it makes you happy. It makes it seem more like a river. This is like art class. All right. Yep. Put a little grass right here. Okay. It's like you're really there. Even draw a sun. That's how I always drew the sun when I was in elementary school, right? Off in the corner. It kind of looks like a sun. All right, it's like you're there at the park on a summer day. All right, and there's a river there. Okay, it says that the river is 1,800 meters wide. All right, so when we say 1,800 meters wide, we mean this direction right here. So I'm going to go ahead and call this delta y. I don't know if I can zoom in much here. All right, 1,800 meters across the river. And so I'm calling that the y direction right there. It then says the velocity of the boat relative to the water. So this is what the boat would travel if the water wasn't moving, and it's going to be moving, is 4 meters per second to the north. All right, so let's go ahead and draw a boat here. I think maybe something like this. It's not going to be very good. All right, and we're saying that its velocity relative to the water. So we're thinking, should I pick a different color here? Or should I stick with black here? I'm going to stick with black here. It's going to be something like this. And this is going to be 4 meters per second. So I'm saying that this is VW, right? The velocity of the boat relative to the water. And it's going to equal 4 meters per second north, right? Okay, so I'll let you jot that down. All right, so we're calling north this direction. And we're going to refer to that as the positive direction. And therefore, east is going to be this way, which the river is going to be moving. And we'll refer to that as the positive x direction. So this is the positive y direction is north, the positive x direction is east. All right. Okay, and then they tell us, and it says the velocity of the boat relative to the water, 4 meters per second north, directed perpendicular to the current. So this is perpendicular to the current because the velocity of the water relative to the shore is going to be moving. I'll use a blue vector for this because this is the water. Is going to be 2 meters per second. So I'm going to draw it a little smaller. 2 meters per second to the east. So we'll call this VW, comma S, the velocity of the water relative to the shore. And we'll say that this is equal to positive 2 meters per second. Okay. And then it says, what is the velocity of the boat relative to the shore? And how long does it take for the boat to cross the river? So we got a couple questions there that we are going to try to answer. And we'll actually answer a couple more than just these two, because sometimes they'll ask us additional questions as well, and I'll point that out along the way. So what is the velocity of the boat relative to the shore? Okay. So the velocity of the boat relative to the shore is the Pythagorean theorem here, is going to be, we're talking about this vector here. Let me go ahead and draw this in. All right, this is the head to tail vector addition. This is, whoops, I wanted a V there. This is the velocity of the boat relative to the shore. Okay, so what we're saying then is, if I write this out down below, and maybe I'll write out the actual words and write it out twice, just so we're clear here. Pythagorean theorem, right, which is a squared plus b squared equals c squared, is the velocity of the boat relative to the shore is equal to, squared, right, is equal to the velocity of, and I can use parentheses here if you like, is equal to the velocity of the boat relative to the water squared plus the velocity of the water relative to the shore squared. And so what I'm saying there is this. I know sometimes these variables get a little confusing. Go ahead and write it out. And kind of when we say shore, what we're saying is if somebody is standing over there on the shore, that's kind of where we're going with that. All right, so we are going to solve this problem by breaking this up into directions, meaning that we are going to work with the y direction independently from the x direction. Okay. I think we could answer the velocity boat relative to the shore part. I think we could answer this yellow question right away using Pythagorean theorem. I'm not denying that, right? We have a right triangle right here. We know two sides. We know the 4. We know the 2. We could get VBS, right? That's easy. We'll do that in a second here. But the second part, how long does it take for the boat to cross the river? So the boat is going to take, when it crosses the river, right, is going to try to go this path, right? The boat wants to try to go like this, directly across the river. However, because of this current that is also affecting the boat, right, going to the right, the boat is actually going to take this path right here as it heads straight across, right? It's going to head straight across, but it's going to move at that diagonal across. And then it'll land on shore some distance, delta x, down the shore. So that's one of the questions that a lot of times they ask in these problems is how far downshore. Another question that we like to ask here is what is this angle that the boat takes? So we're just going to use a lot of our skills here that we've used before. There's not going to be a ton new, right? We'll work in the y direction, x direction independently. and try to solve for these. So I'm just going to go through it, and we'll kind of check off questions as we go. So we're not going to go in any particular order. I'll just show you how I would usually approach this problem, regardless of what they ask us. So one of the first things I like to do is split the problem into the x direction and y direction, and then say, well, which direction should we start with first? And the answer here is, well, what do you know more about? Well, let's look at it, right? If I get my highlighter out, and in the y direction, we know the distance across, and we know the y velocity. In the x direction, we know the x velocity, and we don't know the distance in the x direction. So we're thinking y direction is better here. And when we work with the y direction, we can solve for this y velocity using K2, right? If we look at K2, the first thing we should realize here is that it's not a projectile in the air. So AY is equal to 0, right? So it's not accelerated motion. So our boat is just going to take this constant velocity straight across with a y velocity. So this y velocity right here is not changing, right? It's going to be 4 meters per second the entire time. And we know how far it takes to go straight across the river, right, at this 4 meters per second. It is 1,800. So what I'm saying is by working in this direction, we really have our old formula, which is this is speed equals distance over time. Or this is V equals delta X over T, right? We'll really have our old formula, which is right there. We know that we can rearrange this, right? Instead of V equals delta X over T, we could say T equals delta X over V. So this is the formula we're going to use here, right? We just do the rearranging. You can see it right here. We'll just get T alone, divide both sides by VIY, which we can really just call VY because, once again, there's no accelerating going on, so it's just going to be VY. VIY is the VFY is the y velocity the entire time. So I'm going to go ahead and rewrite this then. So we'll divide both sides by VY, and we're going to get T equals delta Y over VY, right? And so it's interesting how our K formulas just become our non-accelerated formulas from earlier in the year when there's no acceleration, right? And that's what should happen. Plug in what we know. I think this was 1,800. And VY was 4. Do the math there. We get time equal to 450 seconds. Now, this is important. This is the time to cross the river. I don't care that we solved it just looking at the y direction. So what I'm saying is when the boat takes any of these vectors, right? When the boat is just going to take one vector. It's going to take this vector. But the time for the boat to move on this red vector is identical to the time we just solved. That's the key part to understand, right? This is the time, the time we solved is the time to take that red vector. Furthermore, by taking that red vector, that is the same amount of time that the water is going to sweep the boat this way. So we can use that time when we work in the x direction. So I'm saying the time in the y direction is the same as the time in the x direction, is the same as the time in this combined direction. They are all the same time. So that's super useful that we got that 450 seconds, because now we can go to the x direction and carry that over just like we like to do. Time is the link between directions. We can go ahead and solve for how far down the river does the boat land. You know, if you were going to wait for this boat to get there, where on the shore should you stand, right? Where on the shore should you stand to be there when the boat arrives? And that delta x value, let's just use K2 in the x direction, right? But obviously, it's not going to have any acceleration. So that 1/2 ax t squared is just going to be 0. Okay, so it's just using this formula right here, non-accelerated motion. So we can solve for delta x because delta x is equal to the VIX, which is 2 meters per second. That's the current of the water, times 450 seconds, which is going to give us, we can cancel off our seconds there, which is nice, going to give us meters, and we're going to get 900 meters. Okay, so this is where to stand downshore that the boat will arrive. All right, so how far to stand downshore that the boat will arrive, or where the boat will arrive at downshore, downstream. I don't know if downshore, is downshore a word? I don't know if I just made that up. Downstream, whatever, you get the idea. All right, so, okay, let's go ahead and get the other question, which was, so we solved for the green one, right? How long does it take for the boat to cross the river? What is the velocity, VBS, of the boat relative to the shore? Let's go ahead and just do Pythagorean theorem, get the red vector, and that's not an issue at all. So we can say, I think it was VBS, right, squared is equal to, I think we said VB water next, plus V water shore. All right, so we get something like this. VBS squared, whoops, did I write VBB? Is equal to 4 meters per second squared plus 2 meters per second squared, which is going to equal 16 meters squared per second squared plus 4 meters squared per second squared, which is going to be 20. So trying to go too fast here and making mistakes. So when we do that, notice the units are the same here, and that's why we can add those two together. Square root both sides. Which, what is that going to equal? Oh, it's probably going to be something not nice. I think it's 4.47 meters per second, according to my notes. You can always check with your calculator if you don't believe me. All right, so good. So is it a larger velocity than just the boat on its own and the river on its own? Sure, right? It should be. It's the hypotenuse, right? This vector is the hypotenuse. So you can write the Pythagorean theorem, it's interesting, for the 3 vectors, or you could write it for the 3 displacements, meaning you could have used 1800. What was this delta x we solved for? Was it 900? I think it was 900. And another thing you can find is you can find out what this distance is right here. They like to ask, how far did the boat travel? What is that distance right there? And there's 2 ways to get that. Let me show you on a down here. The first, obviously, being the Pythagorean theorem. So we could use delta. So I'm saying I'm going to call that S for spatial displacement or spatial position. I'm going to call this S. So I have S squared. So what I'm trying to say is this. I have S squared is equal to delta y squared plus delta x squared. So you could write the Pythagorean theorem for these distances. Could we call this delta S? I think you can. I'm just going to stick with what I got right now. All right, so I have S squared is equal to 1,800 meters squared plus delta x squared, which I think we said was 900. All right. So S squared is equal to, ooh, the math is going to start to get kind of intense here. Let me grab my calculator. I don't think I did it this way in my notes. I did it a different way. So that's okay. I'm going to show you a couple of ways. So let me just square this really quick. 1,800 squared. All right, that's going to be 3,240,000. All right, plus, what is this one? I think it's 81 followed by 4 zeros. So what would that be? 810,000? All right, and that's going to be meters squared. Okay, so then we'll add those two together. Whoops. Hold on one second. All right. I'm getting 4,050,000. So I could have did that in my head, but oh well. All right. Good. Okay, and that's going to be meters squared. And then we're going to go ahead and square root that. Gives us 212.46. Probably could round to just 212. So there we have it, right? There's another piece of the puzzle we got here, which is how far does the boat travel, which they could ask as well, right? Because we know the boat doesn't go 1,800 meters. It doesn't go 900 meters. Instead, it goes this red dotted line right here, right? Across the river. Because it tries to go straight across, gets pushed by the current at the same time, and ends up taking this red dotted line path, which turns out to be 2,012.46 meters. Now, another way you could have did that, right? Let's think about that. You know the velocity. You know VBS. VBS was it 4.47 or something? 4.47. So I'm saying that you could have used 4.47 meters per second and realized that, well, when it travels 4.47 meters per second, it travels that for that same time, right? That time value was, I don't think I ever wrote it down right here. I think it's down here, 450 seconds. So what if we just work with the same formula we had before, right? Something like, I guess I'm going to write delta here. I'll write delta S. Delta S is equal to VBS, right, which is our velocity of the boat relative to the shore, the red vector, times our time, right? Because this is in the form of delta X equals Vx times T, right? That's kind of where I'm saying, right? This is our K formula, but this is just in that weird direction that's not X or Y. So we can write it like that, all right? So let me just go ahead and put a line through that. That's just there for reference. Okay, so if we do that, then we'll say that delta S then is equal to 4.47 meters per second times 450 seconds. This way is a lot easier because I'm going to just square those crazy numbers. You can call this S if you want, or delta S. Once again, S just stands for spatial position. All right, so 4.47 times 450 is going to give us 2011.5. And so a slight difference, right? Because there is some error involved. And so I think with sig figs, you probably would be rounding a decent amount here and get it closer to 2012 or maybe just 2000. I'm not sure. Anyways, so yeah, so the same answer, which is what we expect. Two different methods, but proving that it's the same thing. All right, one final last question they like to ask, right? So we got 4 questions they could ask, right? So here are the things, when you do these problems, right? They could ask you time across the river. They could ask you how far down shore. They could ask you what is the velocity of the boat relative to the shore, which is that combined velocity. They could ask you how far does the boat travel, which is that S value. So the 4 questions they could ask, right off the bat. And the 5th one is, what is the angle that the boat takes relative to perpendicular, relative to a line straight across, or relative to the shore, right? So what they're asking here is they could ask, what is the angle, which is relative to the shore that the boat takes? So they could ask this. What's this angle right here, right? Or they could ask for this green angle and say, what is the angle to a line straight across? Here is a line straight across, right? A perpendicular line. Let me see if I can get a color. I'm having a hard time choosing a color. Let's go with orange. All right, to a line straight across. Here's a line straight across, right? What is the angle relative to that the boat takes? So that would be that green angle, right? It's kind of, let me see if I can erase something without erasing the entire problem. Okay, yeah, good. I was really worried there. It was like the whole thing was just going to disappear. All right, so we want that green angle there. We want theta, right? And if we wanted the other angle, the complement of theta, we could find that, right? Just 90 minus theta to get that angle, the purple angle with that line through it. All right, so let's go ahead and get this. So we're thinking here inverse tan. Why inverse tan? It's just the one we've gone to the most. And so let's write that formula out. We know how to do inverse tan. Tan theta is equal to op over adjacent, right? TOA, that's where I'm getting that from. I'll write that out. TOA, SOHCAHTOA. This is the TOA part. So hopefully everyone remembers this. TOA, TOA. Okay. But we want inverse tan, so inverse tan eats tan. So we'll go ahead and inverse tan both sides. Just kind of like an undo button of tan. So we destroy tan with that, and we're left with just theta. But we tan inverse the other side, so we have to write that in. And there's our formula right there. Where is our op and adjacent? Let's go up here and look at the green angle, not the purple one. All right, looks like we could use, okay, well, let me write this down first. So I have op being here, right, across from the green angle, and adjacent being here. Now, here's my point. We could use the velocities, or we could use the displacements. Let's look at that. Why is that true? Well, what I'm saying is, you could go one of two ways, right? You could go this way. Using the velocities. Or you could go this way using the displacements. I think it was 900. Yeah. And check that out, right? What's 2 divided by 4? 0.5. What's 900 divided by 1800? 0.5. Units cancel. So, and you never put signs in a tan inverse formula, in my class at least. Either way, it's going to be tan inverse of 0.5. So let's go ahead and type that in our calculator. Hardest part is finding that tan inverse button sometimes. 26.565 is going to be theta. All right, and there's our angle, 26.565 degrees, right? Those are the degree symbol, right? I think I like to write it like this. I like to write downstream from, you could say from perpendicular. I'm going to say from straight across. perpendicular to what? Be perpendicular to the river from straight across. I think that's the easiest. Sometimes when I teach, I do things in a way that I think makes the most sense, not necessarily the way I would always do it, right? And that's, the two are usually the same, but sometimes they're not, just because obviously I'm more comfortable with this stuff because I talk physics, every day. And so it's yeah, I mean, hey, you want to talk physics every day, you can be a physics teacher someday too. And you'll know what I mean. So yeah. Anyways, so there's number 5. So 5 questions that they can, oh, dang, that was supposed to be a highlighter. All right, let me see if I can erase that. Oh, geez. So this is where it starts. I think the eraser gets too big and then it start erasing everything. So the 5th question being, what angle does the boat take relative to perpendicular or relative to the shoreline? If they said relative to the shoreline, what would that be? That would be theta equals, well, we got to do the complement, 90 minus 26.565. Oh, what is that? That's going to be like, that's going to be 63, right? 0.435, I think. Trust my mental math there. I'm going to plug it in the calculator just to confirm, but I'm pretty sure I'm right. All right. Yeah, of course I'm right. All right. Theta equals 63.435 degrees. That would be up from horizontal, or that would be we'd say up from shore or from the shore. 63.435 degrees. I'm trying to describe this purple angle, right? 63.435 degrees from shore. I think that would work, right? Yeah, I think that would be good. All right, so just write that down. Okay, so I kind of like the other one a little bit better. I feel like, I don't know, I almost feel like this one's not quite detailed enough. Maybe, I don't know. Anyways, I think either would be okay. All right, I'm going with it. All right, so I just feel like when we say from shore, it could point differently. It could point upstream. So maybe I need to say downstream from shore. Yeah, I think I like that a little bit better. All right, I think I like that a lot better. All right, so anyways, 5 questions they could ask, right? Well, actually 6 if you think about, how relative you can make those angles. But 5 questions, right? 1, time across, distance, how far downshore to wait for the boat, or where will the boat arrive, velocity of the boat relative to the shore, distance the boat travels, and then the angle the boat takes relative to straight across or relative to the shoreline. And there you have it. I don't think there's anything else to add. But the key idea is draw the picture out, split it into components. It's already done for you. Work with one direction at a time. Get the time links them all the links both directions, and that 450 seconds is the time you're traveling in the X direction, in the Y direction, in the combined directions, which we call it kind of like an S direction for spatial position. But yeah, hopefully that's making sense, and that's all there is to it. So I'll go ahead and stop it there. Have a good day.